but also you can get the book free at the end. So again, these challenges are posted in Facebook, so look for more information there. And lastly, if you're interested in what we're doing as a society and like the events we're doing, we would really appreciate that you would kindly advertise the society to anyone who would be also interested in quantum information, because we're a growing society and we're only our first year. So yeah, this would be really appreciated. And moreover, if you have any ideas for events or want to collaborate, or maybe even give a talk to us, contact us. We're really happy to hear anything from you and do even outreach events or anything like that. In terms, one thing before also introducing the speaker, if you have any questions during the talk, either write them to me or to the chat section, and at the end of the talk we will go through the questions, and if you want, you can ask the question live also. Okay, so I'm really pleased that today we're joined by Professor Alán Aspuru-Guzik, and he's currently a professor of chemistry and computer science at the University of Toronto, which he joined in 2018, and before he was a full professor at Harvard University. It's really amazing to see how many different things Alán is doing. Besides running a group of more than 30 graduates and postdocs, he also finds time to be a faculty member of the Vector Institute, be a co-founder of Zapata Computing, who is the developer of quantum software and algorithms, and also a co-founder of Keybotics, who is a company that focuses on novel materials discovery with use of AI and robotics. Alán is also a recipient of many awards, like Google Focused Award for Quantum Computing, the Sloan Research Fellowship, and he was named one of the best innovators under the age of 35 by MIT Technology Review. And this is just a few awards to name. But nevertheless, Alán's research expertise, which is of course the most important thing, is even more important than his resume. Initially trained as a theoretical chemist at University of California, Berkeley, he now works in the interfaces of quantum information, chemistry, and machine learning. And he is a pioneer in the development of algorithms and experimental implementations of quantum computers and quantum simulators dedicated to chemical systems. And he also does research in other fields, such as automation, autonomous chemical laboratories, artificial intelligence, and materials discovery. So without any further ado, I welcome Professor Alán Aspuru-Guzik to talk about the age of quantum variational algorithms and share his work with us.
Thank you. It's an honor to be here virtually, even with a virtual background. Let me just begin by saying a couple of things. Because I'm not there physically, but I looked at the list of attendees. There's a co-author of mine and great quantum information scientist there, Sam McArdle. I also see Carlos Outerial, which spent some time in my lab. I see my colleague David Clary and others, so David too, so Robert Tiu, sorry. So many thanks for being here, the people that are connected. Okay, so that's the first thing. The second thing is a little advertisement. I'm wearing a t-shirt. For those of you that are interested in creating quantum computing startups, the Creative Destruction Lab at the University of Toronto has a quantum stream, actually the first stream for quantum companies. And you might be interested in actually participating there and actually, commercializing your research. Okay, so that's a very interesting opportunity for people. And of course, our company Zapata Computing is always hiring. So look at the ads of Zapata Computing, and we would love to have more people from this audience, perhaps, as we continue expanding. So those are a couple advertisements, but I'm going to continue doing another advertisement before I give my talk, because this is also relevant to this discussion. And it's the fact that here in the University of Toronto, together with Zapata Computing, we started this seminar speaker series that we conveniently call QRST. I think Matthias de Groot came up with that suggested name. So it's a Quantum Research Seminar Toronto. It's convenient for your time scales. It will be at 4 p.m. Oxford time, I guess. And the next one is going to be May 27. You can go to our Twitter and register. Last time we had a couple hundred people, I forget, a lot of people connected. So you're welcome to participate and listen. The seminars are in an interesting format. It's 2 speakers for roughly half an hour each, because we believe Zoom is hard to listen to for a long time. So those are the advertisements, and I hope I see some of your faces in those talks. They are open to everybody in the planet. Okay, so now in this talk, I have 45 minutes, and I'm going to try to make it even shorter if I can to have time to discuss with you more. I want to talk about variational quantum algorithms, but I decided to focus on one of them. Okay, so I'm going to tell you examples of the variational quantum generator that I developed with my student Jonathan Romero. But he will try to tell you a couple of things, and also I will talk about our code, Tequila. So I am assuming people can see my screen. So here you can see what I like to call sometimes this talk the age of variational quantum algorithms. You can see that there are a lot of different tasks, like minimizing energy, maximizing the cut size of for example, for an optimization problem, minimizing errors or minimizing loss functions that are compatible with the variational theorem of quantum mechanics, right? So you want to maximize a function, and therefore you can use theories such as the variational theorem to actually optimize an ansatz wave function, and then get a better, a lower loss function, for example, or a lower energy. That is important because this unifies a lot of the new algorithms that people are thinking about for near-term intermediate scale quantum computers. And since we introduced the variational quantum eigensolver very early on, and at the same time as Eddie Farhi introduced the QAOA, you could basically say that this has been a huge explosion of all the algorithms that are potentially being thought for near-term quantum computers. So I like to always talk about machine learning nowadays with this example. If you have heard me talk about it before, I apologize, but I like it a lot because it's very current, right? The movie Blade Runner happened originally in fiction, but in November of 2019, so not very long ago. And it was pretty apocalyptic, a little bit our times, and we have, the themes of the movie are artificial intelligence and robotics. So I want to use this because I want to discuss a part of machine learning that I want to go into. So if you haven't seen the movie, you should, first of all. And the second thing is that in the movie, there is this character called Deckard, played by Harrison Ford, whose job is to actually identify and kill androids. So therefore, Deckard is faced with these data points. In this particular case, these people, Batty, Priest, Sebastian, and Rachel, and he has to decide if they are human or androids. Turns out this is the answer, so I'm spoiling a little bit the movie. So he has to kill those three, and he has to spare Sebastian. And the big, I would say, how would you call it, moral conundrum is he himself a human or an android? Okay, so now we're talking about two different types of machine learning tasks here that are relevant to this talk. The first one is, of course, Deckard. He is basically taking care of a machine learning problem called classification or regression. Is this an android or a human? And they could even be in a continuous scale, right? Like 80% sure that they're an android, or 20% sure they're a human, for example. So this kind of regression problem, X, given an X, give me a Y, is one of the most famous problems where people actually do machine learning. But today we'll be talking about another type of machine learning that is very popular, and it's the idea of generative models. Think about the fact that Batty has a much harder job because he has to generate human behavior. So what is a generative model then? A generative model is a model that actually is generating the joint probability distribution of X and Y, right? So it's a little bit more ambitious than just a discriminative model. And you might say, well, Alán, that sounds very esoteric, but we have used all the time in physics and in chemistry and in material science and sorts of other numerical fields, generative models. The most popular, perhaps, is probably the Monte Carlo method, which generates samples from the Boltzmann distribution, and it's employed, every day in the supercomputers around the world. Very simple algorithm, but it's actually generating, samples from a PDF, and that's kind of a generative model looks like. Perhaps the most famous generative models are the generative models that generate images. This is an example. Okay, so there is a website called whichfaceisreal.com where you can actually see these faces. And I invite the audience. I usually do a raise of hands, but here it's very hard. So just raise your hand in your head and think about which of these people are actually people and which of these people are actually digitally generated. And this is the answer. The guy in the left with that crazy hat is a computer dream, but the two people on the center and right are actually real humans. And it gets to the point that it's very hard to figure out who's who. And the way this is done is solving this kind of game theory / machine learning problem called GAN. Okay, which GANs came out around 2014, 6 years ago, and they really took the machine learning community by storm. So the way it works is you have a generator that generates samples. Okay, that will be, for example, in the classical machine learning, a RNN or a LSTM, so recursive neural networks. And the discriminator, usually a convolutional neural network, a discriminative network like the ones we talked about before, that actually figures out if the samples are real or not. And you train them together. The example I like to make is an example of a Mexican robber trying to fake bills for a Mexican cop with the reference data. Okay. I just watched a big series in Netflix called Heist, Spanish. So I'm going to try to make it more Spanish because the Spanish have this beautiful series about robbing the Bank of Spain. Similar. So again, an example is, for example, the PDF of numbers. So you can see here a very famous machine learning database called MNIST, which is basically handwritten numbers that are labeled. So the data in X will be those numbers and the labels will be 0 to 9, and you can see the variability. So you have a probability distribution function over all the possible label data points that are actually these handwritten digits, say for postage. So a discriminative task again will be taking those digits and actually assigning their labels. And a generative model will be start writing numbers, right? Start generating some synthetic numbers that are not exactly in the data set. So in a classical setting, you have a random source of noise that you run by a deterministic function that takes that particular random z vector, okay, and generates a particular number, right? So if you were to move into this particular vector space for this distribution, this joint XY distribution, you will actually start sometimes sampling 3s or 4s or 5s or 6s or 7s. And a lot of the things that you do, for example, in molecular design or other fields, is guide this search, right? Take this particular search in the PDF for a particular member of the distribution, something that I really like to think about when I'm thinking of molecular design, something that will come later. So, again, right, therefore, takes the real data source, okay, this vector X, these are the numbers that come from the distribution of the MNIST database, and takes the classical generator, right, this is the generative function here, and generates these fake ones. And then they are shuffled and shown to the discriminator that has to figure out if they are real, which is this label, or fake, this label, right? So this guy is trying to maximize the fidelity of this discriminator. At the same time, the generator is trying to maximize the probability of generating real numbers, right? And again, this paper by Ian Goodfellow and Joshua Benjo from Montreal really was very important. More formally, right, you are solving this min-max problem, okay, trying to minimize this loss function, maximizing the success of the discriminator, and you use usually gradient descent approaches for images, or you have a policy and then you use a gradient for a policy if you're using something more like reinforcement learning. So what is really cool about it is, I mean, this plot is actually old. We have to update it, but there is this website called the GAN Zoo, where you can see an exponential growth in the number of GAN papers named GANs. And my group has already developed a few GANs, especially in classical molecular simulation. One is called organ, one is called organic. We have developed other GANs within Silico AI and so on. So several GANs that we have developed in my lab already in classical, but also in quantum, and the topic today is quantum. So how can we think about quantum circuits and their connection to potential connection to neural networks, right? So you have to remember that these variational circuits are actually parameterized, right? So you can think about them as neural networks with unitary linear layers acting on 2 to the n nodes, okay? So now what is really cool is that you could imagine that the weight dependence in the gate parameters doesn't necessarily have to be linear. That's going to be important soon, right? So in this paper, the variational quantum generators that Jonathan and I put together in the archive and is going through, it took a while to put in the review process because he moved on to Zapata computing, but now he's submitted. But it was the last paper of his very, productive PhD. What we do is basically use this type of circuitry to generate data set, okay? And then you generate data, and you can certainly, certify it either with a classical or a quantum discriminator. But we'll go through the details of this. But basically, what we want to do is use a part of the circuit to sample from this probability distribution, then a generative piece of the circuit, and then measurement will actually allow us to get these expectation values that are fed into classical neural networks, so to speak, if you want to think about it. So the set of observables, of course, will be Pauli matrices that we're sampling from the quantum computer. The GANs, and maybe this is not even the state of the art, or things move really quickly, but the thing about the GANs is that we were working on this as many others. For example, Pierre-Luc Dallaire-Demers, which was at the time at Xanadu, then he came back to Zapata computing, was working in a particular type of GAN. My colleague and friend Seth Lloyd was working on others. And of course, we have the work of Zheng Zidu, who many other people. So this VQG, what is a little bit different is trying to generate continuous data distributions. And it has the possibility of mixing and matching classical and quantum pieces for the generator and the discriminator. Okay, so we are very inspired by the work of Keisuke Fuji. The first author of this paper that is very important is Mitarai. And what they do that is really cool is that you define a quantum circuit that has all these input parameters theta, okay, and you define a cost function that has these quantum observables, okay. So that's basically the setting that we're working on. But something very important is that you can actually introduce nonlinearities by thinking of these parameters by going through a classical preprocessor. For example, you could have some sort of activation function that makes these parameters kind of nonlinearized, right? So that's kind of like the nice thing about this paper. So again, here is a setup of the GAN. In this particular case, we're going to look at what we like to call in our paper the scheme 1, where we actually have real data and quantum data together. And they pass a classical discriminator, and that will actually allow us to know if it's fake or not. Another cool way of doing this is actually using a quantum discriminator. And this quantum discriminator, what it will actually do is take the output of the classical generator and then discriminate and tell us the probability of being real as expectation value of this single qubit here. Okay, so 1 plus expectation value sigma c of this probe qubit over 2, right? So that will be the probability of being correct or not. So you can train these two things together. So what did we do? Numerically, to test this, I like to always test things numerically. That's something that you guys should do. And nowadays, there are many cool tools to do that. And I'm going to actually use half of my talk or so, or maybe at least 10 minutes of my 45 minutes to talk to you about a new tool from our lab that actually we just introduced that will help with this. Okay, but this was not done with that tool at the moment. So here is the idea. So you have here this circuit that contains these parameters z that are passed by these nonlinear functions. In this case, this cosine, inverse sines and cosines, and then that will be kind of like the generation of the sampling from the distribution passed by the generating circuit that you can see here corresponds to these rotations and these 2 qubit gates, right? So very simple circuit, but the circuit allows us to and again, the nonlinearities where we decided to introduce the nonlinearities over there, but you could change and mix and match here. And the discriminator turns out to be a more complicated circuit that contains an encoder and then this discriminating circuit. So these stencils are something that my student Hannah Shin has studied in another paper of ours. What would be good stencils to employ for these variational circuits? And turns out this is a stencil that is good enough to actually do this task, okay? So if you want to use a classical discriminator, we just used a very simple 2 hidden layer activate, ELU activated function neural network with 1 fully connected layer at the end, as usual. Okay, that takes us 15 neurons to a particular yes/no answer. So you could train with this quantum discriminator, or you could replace it by a neural network. And this type of idea, I mean, is very popular nowadays. I mean, many people, including, I guess, pioneers of that are the researchers at Xanadu that have talked about connecting pieces between classical and quantum neural networks together. So what is really cool about it is that Jonathan was able to actually make this work. Okay, so here is a classical discriminator. We're minimizing the KL divergence between the generated data and the data that is used as a reference. Okay, and you can see here how the loss function also is being converged, right, as it should. And what is really cool also is that although the quantum discriminator network is actually quite simple, you can see the same behavior. So you can plug and play and change the quantum discriminator and the classical discriminator. I haven't told you about what is the distribution that we wanted to sample. So of course you saw very few qubits in this experiment. So this experiment is actually quite simple. But the distribution that we wanted to sample is this kind of 2-finite distribution here that has no other meaning than Jonathan picking the parameters for our circuit like this, 2.48, 2.52, and 2.0. So really, the generating circuit generating this, it has no other meaning whatsoever. But what is really nice is that when you actually start optimizing about 7,000 epochs, these numerical optimization cycles that in machine learning are called epochs, you can actually see the network converge to the answer. So adversarial training with circuits works. So you can see here, again, as you increase the epochs, you can actually see the distribution get closer and closer to the so-called right answer. So some of the things that we're interested on, obviously, is can we use the generator as a piece in a classical neural network setting. So this is something that my lab is exploring a little bit, how to embed, and actually my student Abhinav Anand is having some interesting preliminary results of embedding pieces of quantum machine learning machinery inside of classical machinery. And is there an advantage for that? It's not clear at all. It's just cool. It's fun to do. And we're exploring it, right? Obviously, you can think about what happens when you add noise. This is something that Abhinav, is his first year PhD project, was doing. And you can obviously simulate the noise with these Krauss operators and have like, typical dephasing and relaxation channels. And the way we did it is with this stochastic version of it, where you actually simulate the density operator by an ensemble of wave functions. And what is really nice about it is that if you add, say, amplitude damping, dephasing, and readout noise, you can actually also make the system work. And the reason we wanted to do that is because we wanted to run it on a quantum computer. That was the first project for Abhinav, and we have a draft in my desk, and this is typical COVID busy professor behavior. I haven't edited it in a few weeks, so I apologize it's not on the archive for this talk, but you will see the data set in that archive paper of different epochs run on a Rigetti quantum processor. So I bet there's a lot of young people in this audience right now, and I really want to tell you that it didn't used to be like this when I was young. I mean, Alexei was mentioning that I got the 35 under 35 award. Well, I'm not 35 anymore. Unfortunately, I'm 43 years old. And when we started in 2004 doing quantum computing for chemistry, I never imagined we were going to be so advanced in terms of using quantum computers on the cloud. Okay. And as you probably know, or you might know, my quantum computer company, Zapara Computing, has a product called Orchestra that you guys can actually sign up for the beta tutorials. And in Orchestra, we actually use that tool to actually run in the cloud in several quantum computers. agnostic to different programming interfaces. And this is not an advertisement so much as telling you that the times have changed so much. So now it's time for me to tell you a little bit more about variational quantum algorithms and then move on to Tequila, hopefully. So generative models can be explicit, implicit. They can have different approximate densities, like the variational autoencoder or the Markov chains, like the Boltzmann machines, or even Markov chain Monte Carlo, as we were discussing. So I'm not going to go into too many mathematical details here, but what I want to say is that I'm going to skip some of this. Yeah, what I'm going to say here is that there's another strategy that my lab and I are obsessed with, and I have many people working on this, including my student Douglas. Douglas right now with Matthias de Groot and others are studying this idea of the quantum autoencoder still. So we are obsessed with the idea of the autoencoder. The autoencoder is a way of actually taking quantum information and compressing it into less qubits. Okay, this is an idea for machine learning, also used for generative modeling, that we want to employ. And what is really cool about it is that we have in this, by Ben Schumacher, and you can actually read this book, these very cool theorems of how much you can formally compress a quantum state, and has to do with the entropy of the system, right? The number of distinguishable states that you can have that you can pass through a quantum channel. So this has to do with quantum communication. And what we did is the variational quantum algorithm version of this tool. Okay. So the idea here of an autoencoder is that if you have, for example, information encoded in this register here, is it possible to take a unitary that takes that particular information and passes it through a channel that is compressed, and a channel that we like to call the trash channel or the garbage channel, where you don't want to do anything. Okay, so this is a one-shot compression scheme. Okay, so the way we do it is we have an encoder, which, by the way, happens to be just basically its dagger, or let's say a conjugate circuit will be the decoder. So basically, this is because of the unitarity of quantum information processing. Well, the idea here is that you can perform a very simple swap test of the information that you want to keep as 0, okay, with this particular vector that you could, for example, initialize as 0, okay. And this swap test and optimization on the swap test on this register is what allows us to actually try to preserve this product state here in the intermediate region of the encoder and the autoencoder. So I find this very elegant because the autoencoder has a lot of connections, I think, to many-body modeling as well, where many people in many-body physics are thinking about how to compress quantum states, for example, with tensor networks and things of that sort. Okay, so this paper, I guess this is from a talk somewhere. This is what happens. You get older and older as a professor. You start having this more and more messy slides. I apologize. But this is probably from an APS that I forgot to remove. Look, 2017. I was super excited. I'm super excited about this paper. It's now published in, again, 2018. It took a while to get it published, thanks to reviewer number 4. But in this paper, what we did is we did a classical autoencoder for molecular design. So if you're interested in autoencoders, they are very, very powerful for materials design. Okay. So I'm going to actually show you a little bit about how the quantum autoencoder works in practice. Okay, so in this particular case, you can see again the idea that you are actually going to compute the cost function. In this particular case, is this overlap estimation after doing the swap test with the reference state, and then you try to optimize, get a new set of parameters, and minimize the autoencoder. What's really cool about, to me, for the autoencoders, and that's why I keep talking about it, is the fact that you can connect it again to many body states. So in this work, we wanted to, for example, compress the minimum energy function of the hydrogen atom, so the hydrogen atom in a minimum basis set. So it turns out that in this particular subspace, you can train the autoencoder with 6 points, and then what you encoded is a data set that contains the rest of the points of the potential energy surface. I really love that, because that basically means that those 44 test ground states are actually representatives of this latent space, and shows you how quote unquote, a quantum generative model could generate a potential energy surface. Another cool thing about it is that you can visualize the density operator of this thing, and you can see how, in this 4 to 2 qubit example, you can see here is 4 qubits, 16 states to 4 states, 2 qubits. You can see how we're able to actually take this molecular wave function and compress it to smaller and smaller and smaller examples. Okay, so this is an example of the variational quantum autoencoder. And now I want to skip work on the variational quantum eigensolver, which is usually what I will continue talking in my talk, but rather move on and show you a presentation that, again, my postdoc in my group, Jacob Kotman, did to the QRST group. So I apologize for those that have attended QRST, but you can actually watch his talk in YouTube. It's going to be a much better talk than what I'm going to show you here. But what you can see here, and oh my God, it looks like it's being kind of, sorry, I'm going to go to full screen because I guess slideshow was actually switching slides. So first of all, the first advertisement is you can actually download Tequila. You can download Tequila today. Why is this called Tequila? Tequila is an acronym that I started for my first quantum computing code back in 2004 when we did the first simulation of the hydrogen molecule in a quantum computer. Of course, digitally, there were no real simulators at the time. We wrote the Tequila package. It was called Tony's Quantum Information Library with Alán. So when we're trying to figure out how to name this package, we decided to call it Tequila again. But now it's called, and I'll read you the name of Tequila. It's an acronym that is a little bit like GNU. Tequila is an extensible quantum information and learning architecture. Sumner is the guy that came up with that particular acronym for Tequila. And I want to unveil, because for this talk, we wanted to show you the logo. And what happened here is, damn, I cannot escape this presentation mode here. I'm gonna just show you the logo from my that we literally have already. This is not the logo. This is the logo. So for the first part in the world, everybody can see the Tequila logo. We're very proud of it as well. Okay. So made as of yesterday. So anyway, so what is the general idea of Tequila? And why we really want you guys to think about it, I guess, as part of one of your toolkits. We know there are many toolkits to develop quantum algorithms that are out there, but we believe that the bar has to keep raised. And what Jacob, inspired by this code called Madness, a quantum chemistry package. And again, let me just go back and say Sumner, Teresa, Cyril, Abhinav, Alba, and potentially even other group members. I mean, this is a real group effort. Led by Jacob, but again, Sumner, Teresa, Cyril, Abhinav, Alba are very active. Is that if you write something in the blackboard like this, okay, let's say you wanted to have this particular wave function and this particular generator, this particular unitary, produced by this generator and this parameter theta and so on, and you have a Hamiltonian of this form, and you wanted to minimize, for example, something like the square of the Hamiltonian, okay, over the expectation value of the square, the square of the expectation value of the Hamiltonian, so to speak, sorry, just to be precise. Then you will need to write code that exactly looks like this. So this is actually code that runs in Tequila, okay? So the idea of Tequila is that you take your annotation and your annotations in the blackboard and scribbles and actually write them in an extremely compact quantum algorithm development package. So you want to think about it a little bit as Keras, if you guys know Keras. Keras is like a very high-level tool for machine learning. So I think this is the way you want to think about Tequila, right? Like a very high-level tool. So Tequila obviously is built on the shoulders of giants. It uses, for example, for the chemistry pieces, uses Psi4 and PySCF. For the automatic differentiation, obviously, when you're actually doing this and you want to compute gradients, okay, you need to actually use automatic differentiation. And for that, we use JAX and also for the quantum chemistry pieces, we use OpenFermion. For optimizers, my lab developed a package called Phoenix that we can employ, as well as SciPy, GPyOt, Adam, etc. And then you can run in several different simulators, your favorite simulator as a backend. Okay, so it's kind of a very easy package to use, and I strongly recommend you to think about it. So how does the Tequila work? You have, for example, in this particular case, this Hamiltonian, this variable. Again, if you see the talk of Jacob, probably it's going to be a much better talk than me giving the first time ever talking about Tequila. Okay. What I want to say that is really cool about this idea of getting the gradients is that notice how you can do the derivative of the energy with respect to parameter A is just as simple as this Tequila gradient of E with respect to A. And if you wanted to get, for example, a Hessian, you can just take the first derivative and then differentiate it again. In this particular case, let's say it's not a Hessian, but just a second derivative with respect to a single parameter. Okay. So it's as simple as that, okay? So, and also you can actually decide what is the backend that you're gonna simulate and which quantum computer you would like to run it on, for example. And of course, these are optional parameters that of course have defaults. And again, if you wanted to, for example, simulate a molecule with the Jordan-Wigner transformation in the small basis set and this hydrogen molecule, it literally will take these 5 lines of code to actually generate the unitary of the molecule. In this case, you can see here this addition of the unitary using the generators and the angles, right? So I really believe this is a very, very, very sexy and cool package. How does it work? I will leave it to you for the talk of Jacob. But needless to say, what it's doing under the hood is actually doing a lot of the numerical the analytic differentiation of the expectation values, all just as algebraic differentiation first, in simple JAX, and then that is passed to the expectation values modules later, then compiled. But what is really cool is that a lot of the operations that you do are actually done in an intermediate representation, as it's being quote unquote, so to speak, compiled inside of Tequila, and then therefore Tequila is also very efficient. So we welcome developers. We will release a manual very soon and a small paper describing the project, but we're in full mode advertising it because we really want everybody to join us and continue developing Tequila, which after all is a fantastic drink. And on that note, let me just switch back to the presentation to show you a picture of my research group, and then open up for questions. There are many papers that my group is actually about to release in the archive that I wanted to talk to you about, but the pandemic has made me a very slow paper editor. So my lab is pretty depressed with my turnout in terms of editing papers back and forth. But stay tuned in the archive. I will say there's 4 or 5 really cool quantum computing papers that are going to come out in the next few weeks from my lab. And a couple already came out already that I didn't talk to you about. Mario Kren and Jacob Kotman actually put out a very interesting paper together with me, a very interesting paper on quantum optics, and just stay tuned for more papers. I was able to actually insert a new Tequila logo here. And with that, I think I did take about the 45 minutes that you guys wanted me to talk. It's 10:46. So I'm happy to open for questions or talk about more in detail about anything you want to talk about. Thank you.
Okay, thank you very much for the talk. So if you have any questions, please post it to the chat or send to the host or me. I had one question before we get going. What do you exactly in Tequila input from quantum chemistry programs, and are you optimizing your wave function, or you just find the expectation values for the molecule? So how does that detailedly work?
Okay, so the way it works in say any traditional variational quantum eigensolver workflow is that you will run the classical quantum chemistry package and calculate the so-called integrals, which are the parameters of the Hamiltonian. Okay, so there will be second quantized operators over your fermions that are prefaced by these numbers that are computed by, basically solving molecular interactions between the different orbitals, right? So electron-electron repulsion terms, for example, or electronuclear attraction or kinetic energy. All of that then is massaged from a second quantized Hamiltonian containing those terms on fermions to a Hamiltonian, second quantized Hamiltonian on qubits. Okay, so the transformation from the molecular Hamiltonian to the qubit Hamiltonian can be done in several different ways. But I would say the quantum chemistry, to answer your question specifically, without continuing telling you about variational eigensolver, the quantum chemistry package will get all the way to the integrals level, defining the Hamiltonian. And then Open Fermion, which, by the way, was developed by my former student, it's Ryan Babush at Google, and with a lot of contributions from students from my group as well, like Jonathan Hanna and many others, Ian Kivlichen. That package, what it does, it takes that Hamiltonian and then writes it into a qubit form. And then what Tequila does, it takes that transformed qubit form, okay, and then uses these beautiful new algorithms developed recently to get analytical differentiation of quantum circuits, okay, which, as Jacob Kottman says, is now a must for any type of development framework, right? This has been one of the biggest revolutions in the recent history of variational quantum algorithms, is the idea that you can get gradients, right? And then these analytical gradients of the circuitry, which, as you probably know, they are sometimes done, for example, by getting two measurements, for example, to get one gradient of a particular single qubit gate. All of this gradient tree is actually used in the simulator to continue optimizing the wave function. But not only the simulator, the reason I like to show you that variational quantum generator example, this can also be done in a quantum computer, right? So you can now plug and play quantum computers and simulators and so on, and it is a beautiful world. Yeah.
Okay. Thank you for the answer. And we have one question by Louis Anderson. So maybe he wants to ask in live. So, so if you can speak, Louis, then ask your question.
I'm seeing the questions here. Louis?
Okay, so it seems he doesn't want to say
Okay,
live.
So I'll read it myself. Louis is not speaking. Yeah, so I had slides actually skipped about the Barren plateau. So Louis is talking about, have I seen the results from the Barren plateaus on the quantum algorithms, and what do I think they mean for the field? Well, one of the papers that is in the works in my lab is about this, so I cannot speak too much, otherwise I'm gonna scoop my own group. But I wouldn't be so much worried about the Barren plateaus for several reasons. One of them is, first of all, you can always start optimizing from very good molecular guesses that we know from classical quantum chemistry, in the case of quantum chemistry. And second, there are optimization ways that we are exploring, for example, with Tequila very heavily now, that seem to be able to get around it in many practical cases. So stay tuned for a couple of results from my lab in that area. Actually, this is a collaboration between my lab and Zapata Computing.
Okay.
So Luis, sorry for being mysterious, but I don't want to scoop my own paper.
Okay, we have another question by Lear Christiansen. I'm not sure if I'm pronouncing the name right, but maybe he can ask me the question himself. Okay.
I'll read it myself. So to what extent, if any, do currently available quantum algorithms for quantum chemistry have any advantage over existing classical algorithms for quantum chemistry? How this is likely to evolve? Very good question, Claire. He says he doesn't have access to speak. That's the reason, but it's okay, Claire. Hopefully I read enough your question. Well, let me answer that. There's two types of algorithms for quantum chemistry in a quantum computer. Early on, we introduced with Peter Love and Tony Dutoy and my former advisor, Martin Head-Gordon, back in 2004, it was published in 2005, a very early algorithm based on phase estimation, Sedloy's phase estimation, right? That allows you to get the expectation values of molecules exactly in polynomial time on a quantum computer. That is kick-ass. That is better than any classical computer and that is known to be the case, if you can prepare the ground state or a very good approximation thereof, you can read out the energy in the exact energy in a polynomial time. There's a lot of caveats here, but that is better than a classical computer demonstrably, no problem. Now, probably Laird's question is more about the variational algorithms, 2014. You have to kind of think about the mindset that we were when we developed that. This is primarily the work of Jarrod McLean, Man-Hong Jung in my lab. At the time, we were working with them on figuring out how to do very small quantum computing experiments, 2-qubit experiments, 3-qubit experiments. Actually, Jeremy O'Brien, when he was still a professor, and now he's at PsiQuantum, right? But Jeremy O'Brien had these new optical chips, and we wanted to use them to do quantum chemistry. And we started thinking about what if we, instead of doing all this phase estimation paraphernalia, we just measure the wave function and kind of variationally minimize the energy, okay? By measuring the function and variationally minimizing the energy. When you go into these variational algorithms, then it all depends on how powerful is the ansatz, and connected to the question of Lewis, if you can actually optimize correctly without running into barren plateaus or other problems. So is your ansatz powerful enough in terms of, say, entanglement to beat the classical neural networks? Sorry, the classical tensor networks, for example, which are probably the biggest competitor, right? So you have a tensor network that spreads your quantum many body state that you're running a supercomputer. And the question is, can you get quantum advantage by having, say, 300 qubits with thousands of gates running variational quantum algorithms? I believe the answer of this is yes. There's going to be a quantum computer that's going to be large enough and a circuit that is going to be deep enough in the reasonably near future, right? I'm talking years, okay, where this might happen, okay? But it's not proven yet. Of course, the quantum computers that we have right now cannot run long enough circuits and don't have enough qubits, the right ratio right now to actually do a problem that we cannot run in a classical computer. You've seen recent results, I guess, by many people, where you can keep increasing and increasing the number of qubits and the number of gates to do variational algorithms. By no means they are better than a classical computer. But in the long term, when we have error correction and we have these algorithms like phase estimation working, yes, this is the end of copper cluster. And if you're a classical quantum computing person, you should be thinking about these algorithms. In the meantime, obviously, there is this gray area of the variational algorithms where many people, including Zapata and others, are working, and we're pretty optimistic about it. Okay. Hopefully that answers your question here, Lair. Yeah.
We have a question by Carlos Otteron, and hopefully now he can ask live.
Hola, Carlos.
Can you speak, Carlos?
Can you hear me? Hola, Alán.
Yeah,
Hello,
we can
Alán.
hear
Thank you
you.
very much for the talk. It was really interesting. I had a question regarding variational algorithms in general. I was wondering, what is your perspective as we get to hundreds of qubits? Do you think that for applications in the regime of hundreds of qubits, especially outside of quantum chemistry, where we have physically motivated ansatz, do you think that finding the global minimum could slow down practical advantages of quantum computing?
Well. There's the issue of global versus local optima. That also, of course, is something to be explored. One of the things that the reasons we developed Tequila as well, and my student Sumner Alperin is actually working on, is I told Sumner, your PhD project should be, let's see how far we can go in the classical simulators to explore this question, right? In other words, I want to be able to routinely run 30 qubit variational algorithms, or 20, whatever is the number, in a simulator in my lab, using better and better gradients. And there's many groups like Patrick Coles and others that are doing better and better and finding ways of optimizing. Also, Jens Eisert has beautiful work on this area, minimizing the number of measurements, getting better ways of calculating gradients, ordering terms in your variational ansatz. For example, our friend Artur Ismailov in the University of Toronto has done beautiful work in understanding this type of systems, and also adapt BQE from Sofia Economou and Barnes and coworkers. And Nicholas Mayhall. It's a beautiful algorithm to actually start building your answers in pieces. I think all of those things together will allow us to get to very good wave functions, Carlos. Do I have proofs for this? No, I mean, this is all heuristic type of quantum algorithms, and people are advancing by the day. Another reason that we developed Tequila is because it's very, very hard to put all these algorithms together in a single place. So I implore you, all of you, if you guys are developing quantum algorithms, to consider using Tequila and putting it in there. It's probably an afternoon exercise because the interface is so high level that if you invent something, say this imaginary time evolution, the beautiful work of Oxford, of the group of Sam McArdle and Simon Benjamin and so on, this beautiful algorithm, for example, should be implemented in Tequila, hopefully, if you guys want to do that, or we will try to implement it so that you can baseline and compare all the different algorithms, right? So that's the only way we're going to find out, Carlos, by having a simulator that can optimize many parameters, that can run on the cloud very easily. And this is where Orchestra from Zapata comes in. Many people might not know what Orchestra does. This is a good moment to say that. Maybe you guys can invite Zapata Computing to give you a talk in this seminar series. That might be useful. But what Orchestra does is allows you to run, say, 150,000 calculations with different parameters and spit it out in the database in Tableau and see what happens, right? So for the question that Carlos asked, right, when Zapata does this with clients, because clients, Carlos, you could be a big chemical company that is a client or a whatever, or a materials company that wants to know this answer. To convince you or not convince you otherwise, you need to run a shitload of calculations. And that's what Orchestra is good for. So I would say, take your favorite simulator toolkit. It could even be, Penny Lane, or it could be Tequila. Take your favorite backend. It could be Circ or QuestKit and so on. And you can put it together in that platform and then do all this analysis. So I think the vision that I'm trying to give to you today is quantum computing is becoming a place where software engineering is very important, the same way as quantum chemistry had, where numerical analysis is very important, where a lot of heuristic things are important, like in machine learning. Acceleration is important. So it's a different era where a lot of the things that used to be important are balanced. So of course, pencil and paper is important, but now there's a lot of software gadgetry that needs to be developed as well to be competitive. Sorry for the nuanced answer, Carlos, but to answer your question, let's try it for 20 qubits. That's my goal in a simulator and see what happens. And then we'll see in a quantum computer. And we will only find out when we run it, I think.
Thank you.
Okay, next, there's a question from David Clary. So let's unmute him. Okay, he should be able to speak.
Hi, can you hear me?
Yes.
Alan, thanks for the talk. Your talks are unique like no others. I'd just like to say that it seems to me that an ultimate application of your research is electronic structure, but do you hope for big advances also in quantum dynamics of highly dimensional systems?
So David, yes, there's a long history of this as well. In 2008, one of my first papers out of my research group, together with my student Ivan Casal, now professor in Australia, I gave a project to Ivan. I said, I want to do H plus H2 on a quantum computer. Okay. And we've done a lot of work on and off on that type of problem. The way it's usually thought of is you're going to use a representation, for example, a grid representation, okay? And now you're going to store your wave function in first quantization. You're going to store it like in amplitudes in this grid. But notice that every qubit doubles the resolution of your grid. It's pretty cool. And then you're going to have the electron and the nuclear wave function all fully non-Born-Oppenheimer colliding. We found out that that's kind of like sounds brute force perhaps for people that do quantum dynamics in a classical computer, but avoids the use of potential energy surfaces that are hard to put inside of a quantum computer. And we don't progress in figuring out how to, when we express the potential that way, like e to the IT, e to the IV, when we express the potential that way, we have John Wedge, one of my students, figured out a way of expanding the potential in a soft way so that we don't need too many qubits to represent this diagonal operator. And now people are doing dynamics just to continue this in other bases, for example, plane wave bases and so on. The Google group has thought about ways of doing this. So there is a lot of work in quantum dynamics. Usually the way we think about it, at least in my lab, I think is that probably for that it's better to think about in this more larger basis in terms of number of qubits. But I could certainly send you some papers that show that, of course, there will be a crossover. It will be a larger number of qubits, but there will be a moment where we will be able to do non-Born Oppenheimer or electrons or nuclei in a quantum computer. Now, hopefully I'm alive when that happens. I'm knocking on wood, because obviously the progress is going to take us first through quantum chemistry, small molecules, and so on, and eventually we get there. But definitely, David, there is room for potential even collaborations with the same thing that has happened in the field of quantum chemistry, where the quantum chemists are entering the field and bringing all their expertise. Could happen if people like you were to enter and say, oh my God, look at this Alán's paper from 2008, it's so ridiculous. Let me just use all my knowledge from quantum dynamics, bring it to quantum computing, and then lower all the costs, squash the prefactors. So I think that's what you will be seeing in quantum dynamics more and more. So for all the young people in the audience, this is a perfect project that you can probably try to tackle. And if you're in Oxford, you should go talk to David and others to figure that out.
Thank you.
Okay.
Thank you, David, for coming to.
Now we have a question by Alexei. So he can unmute himself and ask the question.
Oh, I just had a question. It's not rather clear to me. In the case of variational algorithms, how you perform gradient descent? Do you use finite difference methods, which should take ages, if I'm not mistaken?
We have a paper with the story of analytical gradients. So first we started using gradient-less methods like Cobila and they are more like simplex type methods when we started very early on, okay, because we didn't know how to get the gradients. I would say one of the first instances of getting analytical gradients for variational algorithms was done by my group. Actually, Jonathan Romero figured out the gradients for unitary coupled cluster. Just figure out how the circuit looks like, and we have now analytical gradients. But then about a year later, or about a few months later, then the people from Xanadu figured out how to get the gradients analytically, Nathan Killoran and others, how to get the gradients analytically for any circuit, at least the gradients of the 1 qubit gates. Okay, so that took us to a different era where analytical gradients are a given.
They are computed efficiently.
Yes, it's efficiently. There's a polynomial overhead for each gradient. For each gradient, you need to get 2 expectation values now instead of 1. So what Tequila does, for example, is keeps track of all that polynomial explosion of terms in terms of the gradient estimation. So it's not terrible, but obviously, yes, to get a gradient is more costly than to get a function.
All right, thank you very much. I didn't know that.
But check the details. I would say the talk of Jacob might be very useful. We will. You can just check the QRST Twitter, and you can go and listen to his talk in YouTube.
Mm-hmm. All right, thank you very much.
Yeah.
Okay, so we also have a follow-up question from Hilaire Christiansen. So.
Oh shit! It disappeared. Hopefully now he can ask it, because I saw the question disappear. Yeah, Claire.
Oh, hi. Can you hear me now?
I do.
Okay, thanks. Thanks for your previous answer. So I just wanted to follow up to understand what kind of the companies like yours and other kind of software, hardware companies are doing kind of for services for chemical companies. So what are the actual practical services that companies like yours and let's say the hardware companies themselves can provide to chemical companies at the moment, and since that they can't outperform classical hardware yet? So is it just kind of giving the companies an idea of potential technologies and how and sort of getting them ready for the future? Or are there some things that quantum hardware companies can actually give to chemical companies that for their advantage right now?
So now I'm wearing my background of Zapata computing just for fun. Okay, it's pretty cool because I'm gonna wear their hat. Okay, so when I talk to you, I usually try to talk to you as an academic, and now I'm responding for Zapata. So it was fun to put their background. But let's discuss. Yes, there are no applications yet where a quantum computer will give any business advantage to somebody that I know of right away. Some companies are making dangerous claims in that direction. I think Zapata is not the company to make such a claim. Okay.
Sure.
Having said so, if you are a big corporation and you want to think about how can you be disrupted, there are offices in these companies that are looking at all the technologies that you're thinking about. Neuromorphic computers, quantum computers, that could potentially change your business line, right? If you are a big company, you cannot be blindsided. So it is those type of groups in the companies that are currently engaging in the quantum computing companies, such as Zapata. Of course, Zapata is not the only one. You guys in the UK have Riverlane, for example. That's another great company doing similar work. So these companies are doing that kind of work. So having said that, and there's a lot of demand for that, and Zapata has several clients for this. Having said that, what also we see as a business is the need for more and more people to run their quantum computing calculations efficiently. Okay, hence the logo on the lower right-hand side of my screen, right? The orchestra logo. We believe that another thing where you can actually enable the quantum computing community is by giving them, power tools to run the algorithms, right? The equivalent of, say, in machine learning, where people were developing TensorFlow and Keras and PyTorch and this type of tools that allow people to really express their algorithms. That's, for example, the case of Tequila. But not only that, run them, because people run those algorithms, say, on the cloud. How do you run those algorithms on the cloud? How do you run those algorithms on several quantum computers? How you mix and match things? That's what Orchestra is. So I would say companies like ours are thinking of products such as those that could help people around the world, academics and companies that want to do research on their own, and also we can help them do research. Why would they do research? Last question, Claire. They might want to do research because they want to have relevant IP in their narrow subfield, right? So quantum computing for this and this and that, right? They want to have this early IP to give them future advantage. So that's another reason why they engage companies like ours. Another reason why companies like ours exist is they are a little bit like deep minds. All comparisons guarded, hopefully, but I'm not good, but they're a little bit like DeepMind, right? We want to get the top talent in quantum algorithms. There's not that many, and concentrate it in our auspices, right? And then we have this power team of people developing algorithms really quickly with tools like Orchestra, patenting some of them as well, and just keeping that IP as well. So these companies are doing several different things at the same time.
Okay, thanks. That's very helpful.
Yeah. Okay, any other questions? I'm going to change the virtual background now.
Okay, we have a question by Joe Gibbs. So,
okay, Joe, you want to say your question?
Okay, he should be able to speak now.
Hi there, thanks for the interesting talk. I was interested to know how, is it possible that the quantum autoencoder can be used to aid quantum chemistry calculations? Like, can you use it to sort of clean your quantum data before processing at all?
Very good idea, Joe. Exactly. So we are working on those type of ideas. For example, the autoencoder. For example, if you actually want to reduce yourself to a subspace of a particular symmetry or spin or particle number or things like that, you can find analytical quantum autoencoder circuits that do that. So you want to think about getting into a subspace of particular relevance for quantum chemistry or quantum dynamics. Just by symmetries, then you can imagine building an autoencoder architecture that imposes those symmetries. But there might be some other hidden symmetries in your system, say in the many-body part of the wave function or whatever. Those could be discovered by a variational part of the autoencoder, right? So you can have an analytical piece of the autoencoder, then followed by a variational piece of the autoencoder. That what it does is, in some sense, actually just takes you to the right basis where you minimize the number of required quantum resources. So yes, there are people like Giuseppe Carleo and others that have thought of these autoencoders also in the classical simulation setting. So can you use them simulating tensor networks or things like that? So you can think about them, yes, as wave function cleaners, as you correctly say so.
Great, thank you.
Also, I have a question myself. You mentioned during the talk that you have those quantum compressors to kind of reduce your total space of your wave function. Mm-hmm. How flexible are these methods? Can you perform a lot of computations on them and then decompress the wave function to get accurate results? And also, the follow-up would be: are those methods currently used in any classical computations, and how much you can actually compress your data?
Again, so the answer, last page is what I said. There are people like Giuseppe Carleo that are trying to do the autoencoders for compressing classical states, all in a classical computer. So there is a literature that you could go to. I don't know how big it is. I don't follow it as closely, but they do that. In our case, in quantum computers, first of all, you know that by the Schumacher theorem, you know how much you will be able to compress, right? So if in other words, you cannot compress without loss if the compressed channel, when it's dense, right? You might now you have a completely dense density matrix there, right? You're losing some of the entries. Okay, so there's something natural about that. Like you can only compress the wave function to the point that you have basically all of the entries of your density matrix are now non-zero. And after that, what we did done numerics is that you can still keep compressing, and then of course you will get some approximate wave function there. You're asking more about using this for quantum computing, and yes, Hannah Sim, one of my students when she was at Zapata Computing in an internship together with Johnny Olson and others at Zapata, found a way of using this as some sort of compiler, some sort of generator of simpler circuits in that subspace. So you can go to the subspace, run a circuit that is in that subspace, and then come out of the subspace. So that's something that Zapata actually put out there, and it's public, I think, that code base.
So essentially, you would be doing calculations in your subspace, not in your total space.
Yeah, and the question is, of course, when you do that, what is the calculation inside of how the operators look inside of the subspace and things of that sort. So it's not so easy. So we don't do it for electronic structures, say, and things like that routinely. But you can, of course, yes, if you, for example, the symmetry piece is easy, right? And actually, it's connected to a paper called by Sergei Bravi of the Bravi-Kita fame of IBM and others. They call it the tapering of qubits method. It's basically an autoencode, kind of like a way of removing qubits by symmetries. It's connected in some sense spiritually to the autoencoder.
Okay, thank you for your answer. Okay, so it seems we don't have any more answers. So, there's the last one. So maybe let's say
Lyric and Lab. Oh, I don't have a Creative Destruction Lab background. Otherwise, I will show it to you. So when I moved to Toronto, I mean, the Creative Destruction Lab had started the running quantum program by the late Peter Witek, which makes me very sad. Some of you might know is missing in the Himalayas. So whatever you are, Peter, So the late Peter Witek and AJ Agraga had a big vision of perhaps seeding the world with quantum startups. And wonderful companies such as Xanadu came out of that. Okay, so when I got to Toronto, I was too busy with starting Zapata, so I stayed a little bit one step away from the Creative Destruction Labs. Obviously, some of these companies also compete with Zapata. So advice for people that do this is the CDL is a fantastic opportunity to come in with an idea, and over 5 sessions, develop your idea and convert it into a potential business. I actually accepted to work with CDL in the creation of a track called CDL Matter to design materials with AI or materials companies. So if anybody has a materials company, send it to the track and I'm going to help run it with many other advisors. So I'm not going to be in the quantum track, but I'm in the other track. So, but I have a lot of knowledge and information about the CDL. So what happens in the quantum track that is really cool is that there's also a training phase where the people that are interested in doing these companies get trained for a few weeks. And several companies such as D-Wave and Xanadu and Zapata and others, IBM, I think as well, help train the people. So in general, advice for nascent quantum startups is find a niche, right? Because obviously there's already a lot of little companies out there and big companies out there. So you want to think about what is the problem that you will be solving. And some teams that came out of the creative destruction lab are doing really cool stuff. For example, Protein Cure is doing some quantum computing, but also some classical computing related to biophysics. Right, so those kids are super smart. I remember when they contacted me and said, "You want to be my advisor?" And I said, "No, I can't because I'm working with Zapata. I cannot be your advisor." Right, but still, this guy Tomasz and others were really cool, and Tomasz Babiš is his name, I think. So they were very optimistic and excited, and they developed this nice company that is out there raising capital and running and thinking about biophysics. So I recommend that you think about a niche if you want to go to the CDL. I think now some of the sessions will be virtual, unfortunately, but hopefully they're in person. And when they're in person, they're fantastic. So really, and by the way, now there is a CDL Oxford, I think, that's going to come online very soon. By the way, if I'm not incorrect, this is a public talk, so if I'm incorrect, I apologize. But I'm pretty sure. Let me Google. That there's going to be a CDL announced already, or potentially, maybe it was already. Yeah, it's already announced. So the CDL Oxford. So you guys can also go local, okay? So, or you can also come to the Toronto one. I think Quantum is running Toronto, but maybe CDL Oxford also may add some Quantum and so on. So you could do it locally, or you can come to your former colony. We still worship the Queen here, so it should be okay.
Thank you very much.
Yeah.
Okay. There are no questions anymore. Then I would just really want to thank you, Professor Aspuru-Guzik, for your talk. Thank you for sharing your knowledge about your expertise in variational algorithms, and hopefully a lot of people have enjoyed your talk.
Thank you, guys. If you have questions, just shoot me an email, send me a tweet. We'll figure it out, okay? And again, remember, there's always postdoc jobs in my labs. We need super smart people. Apply, right? And there's always jobs at Zapata as well. Check out the jobs, okay? So take care.
Okay. Thank you very much. Have a nice day. Okay. Bye.